You know that feeling, right? That little moment of panic when your internet just stops? Well, it's not always just a problem with your Wi-Fi. Sometimes one single misconfiguration, one tiny error somewhere out there, can sever the digital lifeline for millions of people all at once. And I'm not being dramatic. Just look at the 2022 Rogers outage up in Canada. This whole thing started with a single flawed update that just snowballed through their entire system. And suddenly, the country's digital fabric just ripped. I mean, imagine this. You have an emergency. You need to call 911, and you can't. You run to an ATM to get cash. Nope, offline. You try to pay for your groceries, and all the payment machines are dead. This wasn't some disaster movie. It was a real and frankly terrifying reminder of just how much we depend on this invisible system we almost never think about.
So, yeah, that brings us to the big question for this whole explainer. How does this thing actually work? This invisible, absolutely essential system that powers pretty much everything we do. Let's pull back the curtain and break it down.
All right, so let's start at square one with your data's digital journey. Because before we can even begin to understand how millions of computers connect, we first have to figure out how just two of them talk to each other. These are the absolute fundamentals, the building blocks.
And the unsung hero of this whole operation? It's the humble data packet. See, when you send a photo to a friend, it doesn't travel as one giant file. That would be like trying to mail a car. It's just not going to work. Instead, your device is smart. It breaks that photo down into thousands of tiny, manageable chunks. These are the packets. Each one is like a single puzzle piece, ready to be put back together on the other side.
So this whole journey is basically a three-step dance. Step one, your file gets broken down into all those little packets. Step two, the packets are sent out. And here is the truly amazing part. They don't even have to travel together. They can take totally different routes across the internet to avoid digital traffic jams. Finally, step three, the computer on the other end catches them all and, like a master puzzle solver, reassembles them in the exact right order. It's an incredible system built for speed and, more importantly, for resilience. But how do these packets know where to go? I mean, they need some direction, right? Well, that's where the hardware comes in. Think of a router as the air traffic controller for your data. It's what connects your private home network to the massive public internet. Then you've got the switch. A switch is more like a local mail sorter for an office building. It makes sure that the file you're sending to the printer actually goes to the printer and not to your coworker's laptop by mistake. And finally, you have the NIC, or Network Interface Card. This is basically the universal translator. It's the physical port or chip that actually lets your device speak the language of the network in the first place.
Okay, so we've got the packets and we've got the hardware to direct them. But how do you actually connect all that hardware together? Well, it turns out the layout of the network is just as important as the gear itself. We're talking about the architectural blueprints for the network.
Now, these network blueprints have a fancy technical name, topologies. But don't let the jargon scare you off. A topology is really just the floor plan for the network. It defines how everything is connected, and it dictates the paths that your data can take to get from A to B. So first up is the simplest design you can have, the bus topology. Just picture one long cable running through a room, and every single computer taps right into it. The upside, it's super cheap and incredibly easy to set up, but it has a massive, glaring weakness. If somebody accidentally trips and unplugs that one main cable, the entire network goes down. It is the literal definition of putting all your eggs in one basket. Now, to fix that very big problem, we have the star topology. And this is what most of us are using today in our homes and offices. In this layout, every single device gets its own private cable connected to a central hub or a switch. The benefit here is huge. If one cable fails, only that one device goes offline. Everybody else keeps on working just fine. The trade-off, as you could probably guess, is money. More cables and a central piece of hardware make it more expensive, but it's a much, much safer bet. And finally, there's the ring topology. In this setup, devices are linked in a circle, and the data travels around in just one direction, kind of like a high-speed train on a circular track. This is great because it prevents data collisions, where packets might crash into each other, so it can be really fast. But can you spot the weakness? Yep, just like the bus, if even one device or one cable in that ring breaks, the whole circle is broken, and the network grinds to a halt. And of course, hanging over all of these layouts is that classic choice we all face: wired or wireless. A physical Ethernet cable is almost always going to give you better speed, more stability, and more security. But let's be honest, you just can't beat the pure convenience of Wi-Fi.
There's no single right answer here. It's always this constant balancing act between raw performance and just, everyday ease of use. All right, so we've got our building blocks and we have our blueprints. So let's talk about scale. How do we go from a little network connecting a few devices in your room to a network that connects the entire planet? Well, networks kind of grow in layers of scale. It all starts with a WPAN, a wireless personal area network. That's just your personal bubble of devices, your phone talking to your Bluetooth headphones, for instance. Zoom out a bit and you have a LAN, a local area network. This covers a single building, like your home, your school, or your office. But the real magic happens when you start connecting all those LANs together, across cities and countries and even oceans. That's a WAN, a wide area network. And the biggest, most mind-boggling WAN of them all, you guessed it, that's the internet. And this is where things get really clever. So how do you safely get into your private office network, your LAN, while you're out using the public internet, the WAN? As zoologist Bill Sellers puts it here, you use a VPN, a virtual private network. A VPN basically creates a secure, encrypted tunnel through the public internet that connects you directly and safely to your private network. It's like having your own secret passage that makes it feel like you're sitting right at your desk, even if you're on the other side of the world. So we've got the hardware, we've got the layouts, we've got the scale, but there's one more really important piece to this puzzle: the rules of engagement. In other words, who's in charge of all the data? And this brings us to the two main models for how a network can be managed. So this really comes down to two totally different philosophies. First, you have the client-server model. Think of it like a bank. There's one central, powerful server that holds all the information, manages security, and makes all the rules. When you visit a website, your computer is the client asking that server for data. It's centralized, it's controlled, it's secure. The other model is peer-to-peer, or P2P. This is more like a potluck dinner. There's no central boss. Everyone just brings something to the table and shares it directly with everyone else. It's decentralized and really resilient, which is why it's so popular for things like file sharing. But you wouldn't want to book a flight on a P2P network, right? For that, you need one official source of truth. Okay, we have covered a lot of ground, from packets to topologies to network models. So let's bring this all home and talk about the big takeaway. Why does any of this technical stuff actually matter to you? Well, beyond just, understanding the modern world, this knowledge has very real-world value. The people who design, build, and maintain these complex networks are absolutely essential to our entire economy, and getting started in this field might be more achievable than you think. There are really two core industry-standard certifications, the CompTIA Network Plus and the Cisco CCNA, that can be the gateway to a career as a network specialist. But on a more fundamental level, it all comes back to this. After seeing how a network is actually built, piece by piece, you start to realize that reliability isn't an accident. It's not a bonus feature you hope for. It has to be designed into the system from the very beginning. With backup paths and fail-safes, it has to be the plan. And that really brings us to a final thought for you. We've seen that pretty much every decision in networking is a series of trade-offs. You can't always have everything. So I want you to think about your own digital life. For the services you rely on every single day, what's the top priority? Is it raw speed? Is it ironclad security? Or is it pure rock-solid reliability? It's a choice we're all constantly making, whether we realize it or not.